Welcome to AI Paper Slop. Today we're looking at a paper called SimpleOPD, which is simple tokenizer-agnostic on-policy distillation for long context reasoning.
Yeah, this one is by the SuO1 team over at the Shanghai Artificial Intelligence Laboratory.
Right. And if you are out there building or, fine-tuning large language models, here is the 60-second core insight from this one.
Go for it.
So on-policy distillation OPD is highly effective for transferring reasoning skills from a massive teacher model to a smaller student model.
Exactly. It's the gold standard right now.
But it breaks down completely if those two models use different tokenizers or if they have vastly different context length capacities.
Which they almost always do.
Right. So SimpleOPD solves this by moving the distillation process out of the latent space and into a shared plain text space.
Yeah, aligning the probabilities only when the exact text strings match up.
Exactly. And to prevent the student model from basically spiraling into these infinite loops, which they call length explosion, they use this clever termination token masking and a reference KL divergence loss.
The results they got with this are just wild.
Yeah, they are phenomenal. Using this method, a 30 billion parameter student model, Intern S2 Preview, improved its ProofBench score by 21.2 points.
That is a massive jump.
It jumped to 55.2, which actually outperforms closed-source frontier models like Gemini 2.5 Pro and GPT-5 at mathematical proofs.
Which is just crazy for a 30 billion parameter model.
Right. So we now have this blueprint to efficiently transfer elite reasoning across totally different model families. Let's get into the mechanics of how they actually pulled this off.
Yeah, so to understand why this shared text-based alignment is such a big deal, we kind of have to look at why standard on-policy distillation is so incredibly hard to scale across different architectures in the first place.
Right, because, OPD is the go-to in post-training right now.
It is.
Yeah.
Like in older off-policy methods, you would just prompt a massive teacher model to generate a bunch of, high-quality answers.
Like just dumping out correct trajectories.
Right. And then you run supervised fine-tuning on the student using those answers. But the problem there is the student is forced to memorize a reasoning path that might be totally incompatible with its own internal parameters.
It's mimicking the output without actually having the underlying latent capacity to understand it.
Exactly. You're tracing a masterpiece, but you don't know how to hold a paintbrush.
Right.
But with on-policy distillation, the student actually generates its own trajectory based on its current policy. And then the teacher evaluates that specific trajectory step by step.
So you're scoring the student's actual thought process in real time.
Yes. That token-level supervision is grounded in the student's active policy distribution, which drastically reduces catastrophic forgetting.
It just makes it generalize so much better to out-of-distribution prompts.
But, and here's the catch, the Shanghai AI lab team hit two massive architectural roadblocks when they tried to use this to distill their elite math model, SuO1, into these smaller open-weight models.
And the first roadblock is just the tokenizer mismatch, right? This is a fundamental structural incompatibility.
Oh, entirely.
But let's say your teacher uses a byte pair encoding tokenizer, like BPE, and the student uses sentence piece.
Yeah, they segment the exact same math equation into entirely different subword chunks.
Right. So if the student tokenizes a string into 3 distinct tokens and the teacher makes it 5 tokens, you can't map the teacher's probability distribution onto the student's output.
No, there's no one-to-one relationship in the loss function anymore. It just breaks.
Which brings us to the second roadblock, which is the context length mismatch. This creates some serious behavioral divergence.
Yeah, because the teacher model here, SuO1, is like an IMO gold medal level reasoning model. It's conditioned to think for tens of thousands or even over 100,000 tokens before it gives an answer.
It's mapping out these highly complex, multi-step logical dependencies.
Right. But the student model, just by design, has a much stricter, shorter context budget.
And this mismatch leads to, the most fascinating failure mode they documented in the paper.
Oh, the length explosion. It's so funny, but also terrifying from an engineering standpoint.
Right. When they tried standard OPD without the new stabilization tricks, the student models just suffered from this length explosion. It's like a chess grandmaster trying to mentor a total novice.
That's a great way to look at it.
But they don't speak the same language, which is the tokenizer mismatch. And the grandmaster expects the novice to calculate 50 moves deep, which is the context length mismatch.
So the novice's brain just completely short circuits under the pressure.
Yeah. And the mechanical reason for this short-circuiting is rooted in how the teacher's value network scores the trajectory, right?
Exactly. Because the teacher is conditioned to generate these incredibly long chains of thought, its internal value estimation heavily penalizes any attempt to end the sequence early.
It hates stopping.
It really does. If the student tries to output a termination token because it hit its context limit, the teacher assigns a massive negative reward to that token.
The teacher is essentially screaming, like, you've only reasoned for 2,000 tokens, the proof needs 10,000, keep going.
Yeah, so the student learns that stopping is basically the worst possible action it can take.
Which gives you models that are practically begging to stop, but are mathematically forbidden from doing so.
The appendix of the paper details these failure modes, and they are incredibly revealing.
Yeah, case A is wild. The student model actually solves an A math problem perfectly. It gets the correct final answer of 279.
But because the teacher's gradients penalize the end-of-sequence token, the student gets stuck repeating this 10-sentence self-check paragraph.
It just outputs variations of, I will now verify the solution is comprehensive 972 times.
Just rambling endlessly.
Until it hits 160,000 token hard limit and the system forcefully truncates it.
And then case B is an even more catastrophic collapse. The model attempts this exotic integers number theory problem.
Right.
It does some initial algebraic reasoning, but then it gets confused, calculating a multiplicative order. And since it can't resolve the logic, and it's not allowed to stop.
The policy just collapses into a single token feedback loop.
Yeah, it outputs the number 2, followed by a question mark, over 34,000 times in a row.
Just generating 2 indefinitely.
The novice chess player just staring at the board, repeating checkmate 34,000 times because the grandmaster won't let them leave.
It's so good. So how does SimpleOPD solve this structural nightmare? The first major fix is Cross-Tokenizer Alignment.
Right. They bypass the vocabulary barrier entirely. They don't try to construct some complex artificial mapping matrix between the tokenizers.
Because that usually destroys the nuance of the probability distribution anyway, right?
Exactly. So they step completely out of the latent space and move the alignment into a shared text space.
It's actually a really elegant process. First, they let the student model generate a response using its own policy and tokenizer.
Yeah, and then they decode that sequence of student tokens back into raw, plain text UTF-8 strings.
Just raw text?
Just raw text. Then they take that exact raw text and feed it to the teacher model and let the teacher tokenize it natively using its own vocabulary.
So now both neural networks have processed the exact same surface level string. They've just chunked it up according to their distinct internal architectures.
Right.
But wait, we have the same text, but the chunks still don't align. The student might have 500 tokens and the teacher might have 480.
Yeah, they're out of sync.
So how do they actually compute the policy update step if the positions don't line up?
They use this linear two-pointer scan algorithm. Imagine 2 pointers moving simultaneously along arrays of token strings. Pointer E is for the student sequence, and pointer J is for the teacher sequence.
Okay, keeping track of where both models are in the text.
Exactly. And the algorithm only aligns a teacher position and a student position if 2 strict conditions are met.
What are they?
First, both tokenizations must have consumed the exact same prefix of the raw response up to that point. No trailing characters left over on either side.
Got it. So the history has to match perfectly.
Yes. And second, the current token for both models has to contribute the exact same text span to the overall string.
So if both the historical prefix and the current text span match perfectly, the student token inherits the teacher's log probability.
Exactly. And that signal is what's used to compute the advantage for the policy update.
But wait, if they're only updating the policy on perfect span matches and these tokenizers are fundamentally different, there have to be massive gaps where the pointers don't align, right?
Oh, for sure.
So what happens to the loss function on those unaligned tokens?
For any unmatched positions, the objective function just falls back to the student's pre-update log probability.
Oh, interesting.
Yeah. By substituting the student's own reference probability in place of the teacher's missing signal, the algorithm effectively zeroes out the advantage for that specific token.
Meaning the model's policy isn't pushed one way or the other by the teacher at that exact microstep. It just stays where it is.
Right. It maintains its current state.
But that seems like a massive compromise. I mean, if we are zeroing out the advantage on every unmatched token, aren't we throwing away the dense token-level supervision that makes OPD so powerful?
Yeah, aren't we just crippling the training?
Exactly. Discarding all that signal seems counterproductive.
It's a highly intuitive concern, but the authors actually anticipated it. They did a really detailed analysis of the lexical overlap between different tokenizers.
Right, figure 9 in the paper.
Yeah, and it reveals something fascinating about the structural nature of language models. In practice, the aligned token ratio starts quite high, often around 90%.
Wow, that high.
Yeah, and it actually increases as the distillation training progresses. It frequently stabilizes around 98%.
Wait, how is a 98% overlap even possible between totally different tokenization algorithms?
Because the boundaries of subword tokens naturally align at white space, punctuation marks, and common structural formats.
Especially within mathematical proofs, I imagine.
Exactly. Even if a BPE model and a sentence piece model handle some complex rare word differently, they both agree on the spaces, the paragraph breaks, the numbers, the equation formatting.
Oh, that makes total sense. So the partial alignment preserves a massive amount of usable training signal.
Right. It proves we don't need identical vocabularies to transfer the underlying logic.
Okay, so we've aligned the text, but that doesn't solve our infinite loop problem. The student is still generating tokens, and the teacher is still heavily penalizing any attempt to stop.
Yeah, it's still going to spit out 34,000 question marks.
Right, so how does SimpleOPD actually prevent the length explosion physically?
They implement two crucial stabilization techniques. The first directly targets the reward model's punishment of the stopping condition. They use special token masking.
Okay, so because the long context teacher model assigns a massive negative advantage to termination tags, like the think tag or the amend tag, they just manually intervene.
Yeah, they simply apply a mask to the OPD loss, specifically on those structural termination tokens.
They set the loss weight for the ES token to 0, basically blinding the student to the teacher's opinion on when the proof should end.
Exactly. Let the student rely entirely on his own internal context budget to decide when the logic is done.
Okay, but the paper notes that masking alone wasn't enough.
No, it wasn't. When they relied just on masking, the truncation rate, which is how often the model hits the hard token limit and gets cut off, it dropped initially, but then it spiked again later in training.
So masking treats a symptom, but it doesn't address the root cause, which is policy drift.
Right. The student is still trying to mimic the teacher's incredibly long reasoning style. So over thousands of training steps, its internal distribution drifts further and further away from its capacity limits until it breaks.
Which brings us to the second stabilization trick, the reference KL divergence loss.
Yes, KL divergence. It acts as a statistical penalty term within the proximal policy optimization objective, the PPO.
It measures the distance between two probability distributions, right?
Exactly. So here, the algorithm calculates the distance between the student's current updating policy and its original pre-trained policy baseline.
Okay, so if the student's new policy starts drifting too far into the teacher's ultra-long context behavior, the KL penalty increases.
And mathematically drags the student back toward its original identity.
It functions like an elastic band anchoring the student to its pre-trained baseline. But wait, doesn't that introduce a massive optimization trade-off?
It does.
Because if we strictly anchor the student to its original self with a harsh KL penalty, we restrict how much advanced reasoning it can actually absorb from the teacher.
Yeah, we want it to learn to be a grandmaster. We don't want it permanently tethered to its novice behaviors.
So how do they balance that?
The authors did a really thorough ablation study on this using the GLM 4.7 model. They tested various coefficients for the KL penalty to find the mathematical sweet spot.
The Goldilocks zone.
Exactly. When they set the coefficient to 0.5, the elastic band was too loose. The model absorbed a ton of knowledge initially, but the policy became unstable.
It started rambling again.
Yeah, leading to high truncation rates.
Hmm.
But when they increased the coefficient to 1.2, the band was too tight.
So it stayed perfectly stable and concise, but the learning was bottlenecked.
Right, resulting in suboptimal benchmark scores. They needed to find the exact threshold where stability and knowledge transfer intersect.
And they found that a coefficient of exactly 1.0 balanced the equation perfectly.
It allowed the model to integrate the teacher's advanced proof pathways without shattering its own internal context limits.
The model stopped rambling and just started generating concise, complete, highly accurate proofs.
Yeah, and the integration of that shared text alignment plus those two stabilization techniques leads to some of the most impressive benchmark gains in recent post-training literature.
Let's talk about those numbers, because they took the 30 billion parameter SU01 teacher model and distilled it into the intern S2 preview student model.
Right.
And on ProofBench, which rigorously tests formal mathematical reasoning, The student model exploded from a baseline score of 34.0 all the way up to 55.2.
That is a 21.2-point absolute improvement.
Which is wild. And to place that 55.2 score in context, intern S2 is a relatively small open-weight model.
Yeah, 30 billion parameters is compact by today's standards.
But under the exact same evaluation settings, Google's closed-source Gemini 2.5 Pro scored 47.2.
Wow.
And OpenAI's GPT-5 scored 39.5.
That's just crazy. This distillation method allowed this compact, highly efficient architecture to comfortably outperform frontier giants in complex math proofs.
And it's completely architecture agnostic. They proved this wasn't just an artifact of the Quinn family by applying SimpleOPD to GLM 4.7, which relies on a completely different BPE vocabulary.
Right, and to Gemma 4, which utilizes a totally different sentence piece tokenizer.
And both of those models saw massive gains on ProofBench, too. The underlying logic maps perfectly across entirely alien neural architectures.
But the most profound finding in this paper isn't even the math scores. No, it's the out-of-domain generalization.
Oh, right, the physics stuff.
Yeah. The distillation trained dataset was exclusively comprised of mathematical reasoning and formal proofs.
Absolutely no physics data.
No biology, no general science, nothing included in the alignment process. Yet, when they evaluated the distilled intern model on scientific reasoning benchmarks like HLE and HIFO, which is this incredibly difficult high school physics Olympiad benchmark,
the model's performance improved significantly.
Yeah. On the HIFO physics benchmark, the 30 billion parameter student actually outperformed its own teacher model, SU01.
Wait, really? It beat the teacher on physics after only being trained on math?
Yes,
Yeah.
which completely redefines what we think these models are actually memorizing during reinforcement learning and distillation.
It strongly suggests that training a model on mathematical proofs isn't just teaching it how to mechanically manipulate algebraic symbols.
Exactly. It is constructing a generalized cognitive scaffolding.
It's learning the fundamental process of building a directed acyclic graph of logic tracking states, verifying dependencies, and structuring an argument.
And once that scaffolding is embedded in the policy, the model can spontaneously apply it to high-level physics or frontier science.
Outperforming the teacher because the student retained its own unique base knowledge of physics facts.
You're successfully transferring the structural mechanics of reasoning rather than simply transferring domain-specific data.
That is mind-blowing. And this observation actually directly influenced how they optimized the data mixtures for the distillation process, right?
Yeah, because you might intuitively assume that to maximize the student's mathematical reasoning, you should expose it to as much diverse math data as possible during the OPD phase.
Right. If the goal is a higher ProofBench score, dumping every verifiable math dataset into the training run seems like the logical choice.
But the paper reveals this really counterintuitive dynamic. They did an experiment where they mixed standard, verifiable math data like problems that have a single algorithmic numerical answer alongside the natural language proof data.
Okay. And what happened?
When they introduced the verifiable math data, the student's ProofBench score did not increase. It actually plummeted from 44.5 down to 38.5.
Wait, adding mathematical data severely degraded its ability to perform mathematical proofs?
Yes.
Why does verifiable math dilute the signal so aggressively?
Because verifiable math data frequently relies on short algorithmic shortcuts to reach numerical output. It teaches the policy to rush to the final answer.
Whereas natural language proofs require methodical, multi-step logical articulation.
Right. So when you mix the two, the policy receives conflicting reward signals. The model learns to prioritize reaching an answer quickly over building a rigorous logical argument.
Which completely destroys its performance on complex proof evaluations.
Exactly. The training data has to remain laser-focused on the structural process of proofs.
And this requirement for deep methodical logic is also reflected in their context length experiments.
Oh, for sure. They tested how the length of the rollout window, the number of tokens the student is allowed to generate during the trajectory phase, impacted the final quality.
And when they restricted the rollout window to 6,000 tokens, the model improved, but the gains were just moderate.
Yeah, but when they expanded the rollout length to 32,000 tokens, the benchmark scores were significantly higher across the board.
Because a 6,000 token window simply isn't wide enough to capture the complex behavioral dependencies required for elite proof construction.
Right. If the trajectory is artificially truncated, the student only learns fragmented pieces of the teacher's logic.
You can't take computational shortcuts when transferring reasoning. The student must generate long, unbroken trajectories to map the full cognitive scaffolding.
But that raises a practical issue, right? If the 32,000 token window is optimal, what happens when researchers hit a wall with compute limitations?
Because not everyone has the hardware to run a massive teacher model for 32,000 tokens per trajectory.
Exactly. And that is the exact bottleneck the researchers tested next in their final experiment with DeepSeek V4 Flash.
They wanted to push the absolute limits of this text-based alignment protocol, so they swapped out their 30 billion parameter teacher for the massive 158 billion parameter DeepSeek V4 Flash model.
And operating a 158 billion parameter model for on-policy distillation is incredibly computationally expensive.
Very expensive.
So due to those hardware constraints, they were forced to restrict the distillation length to that suboptimal 6,000 token window.
Right. But despite that short trajectory limitation, distilling DeepSeek into the intern S2 student using SimpleOPD still yielded an 18-point gain on ProofBench.
And a 9-point absolute gain on the AME 25 benchmark.
The efficiency of the shared text alignment protocol allowed them to extract immense value from a frontier model, even under strict compute limitations.
That's super impressive.
It really is.
Yeah.
So, that wraps up the operational mechanics of SimpleOPD. For the researchers and engineers out there listening, this fundamentally alters the post-training landscape.
It absolutely does.
We are no longer bottlenecked by shared vocabularies. We don't require identical parameter architectures. And we have a proven mathematical framework to bypass those catastrophic length explosions.
Yeah, by moving the alignment into a plain text space, masking the structural termination tokens, and anchoring the policy with a KL divergence penalty.
We can efficiently upgrade small, highly deployable models by extracting the deep reasoning pathways from these state-of-the-art giants.
And to conclude our analysis, there is this profound theoretical implication hidden within these mechanics that I think is just fascinating.
Oh, let's hear it.
SimpleOPD demonstrates conclusively that dense token-level policy distillation does not require a shared latent space.
Right.
We're successfully aligning and instilling deep cognitive frameworks between two utterly alien neural architectures using nothing more than raw surface-level text span.
Just UTF-8 strings.
Just text. So if the proximal policy optimization algorithm can extract elite reasoning purely from text span alignment, it raises the possibility of bypassing the AI teacher entirely.
Wait, what do you mean?
Imagine engineering an interface that pipes a human mathematician's live, keystroke by keystroke, text edits, backspaces, pauses, and structural reformations directly into the PPO loss function of a reinforcement learning loop.
Oh, wow.
You would effectively transform the human mind into the teacher model. You'd be natively distilling human cognitive scaffolding straight into the neural network's policy, completely unhindered by architectural language barriers.
We are literally building the infrastructure to distill human reasoning directly into the loss function. That is why we track this research. That concludes our analysis for today on AI paper slop. Keep your tokenizers mismatched and your KL divergence grounded. We will see you next time.